Hello everyone. In the previous class, we have seen what an embedded system is and how it is different from general computing systems. And we have also seen the classification of embedded systems and major application areas of embedded systems. Next topic that we have is a very important thing, that is the typical embedded system. So it can also be asked in the exam, like elements of an embedded system. What are the elements of an embedded system? Okay, so a typical embedded system consists of these elements. You can see there will be a system core, right? There will be a system core. Then there will be some inputs and output ports. Input ports, as you have seen in the previous case, they are sensors actually, and output ports, they are connected to the actuators. Then there will be a memory. Why there is a need of memory is, we know embedded system is a combination of hardware and software, that is actually the firmware. So where the firmware has to be stored, it is stored in the memory. Okay, so there'll be an inbuilt memory, a small memory. Then some communication interface, may be wired or wireless. They may be onboard or external communication interfaces. Examples are Bluetooth or USB, okay, or Wi-Fi, or serial ports, parallel ports. It could be any of these communication interfaces. Then there are some other supporting integrated circuits and subsystems other than this, like it might be a reset circuit, okay, or a watchdog timer. So different things apart from these things. Now coming to the central part of an embedded system, we have core, the system core. So the core of an embedded system, it can be a microprocessor or a microcontroller. Apart from this, it can also be an FPGA, that is field programmable gate array, or it can be an ASIC, that is application specific integrated circuit, or it could be a DSP, that is digital signal processor, or SoC, that is system on chip. Okay, so the next thing is the memory. It can be RAM or ROM or both. Okay, so both are actually present, some part of RAM and some ROM. Then the software that is put into the memory, into the ROM actually. Then the communication interfaces, then different types of sensors to detect the changes in the input variables, then actuators to cause the changes in the output. Okay, so we will see one by one. Yeah, the elements of an embedded system, it actually contains a single chip controller which acts as the master brain. The controller, it can be a microprocessor or a microcontroller or FPGA or ASIC or DSP. Okay, so ASIC, ASIC is application specific integrated circuit, or we also have another thing called application specific standard product, okay, which are readily available in the market and you can use them. So all these things, they are very distinct things. So each of them, microprocessor, it has just got a processor on a single chip, but other things which are required, they have to be added externally, like maybe input and output ports, or some interrupt controllers, okay, and timers and other things whatever are required, even memory, they have to be added externally. Whereas if you use a microcontroller, it will have its own input output ports and some memory along with that. Then there are things called FPGA, field programmable gate array, okay, which you might have studied in your HDL lab. Then digital signal processor, which also you have studied, okay. Then ASIC and ASSP. So where there will be a specific IC for one particular application, you can program it and use it for one particular application. So normally these embedded systems, as seen in the previous case, they are reactive systems. Reactive systems means, so there will be some action happening and the embedded system will react to that particular thing. So that action may be some change in some parameters which are detected by the input ports, that is sensors. Okay, so it could be some change in the temperature, or it could be some particular action that has happened, after which embedded system has to react. Okay, so they are reactive systems. The control is achieved by processing the information coming from sensors and user interfaces. So if you normally they will have user interface, as we see. So a particular a user, if he presses a particular button, some action has to happen, so that way. Okay, so there will be reactive systems and controlling some actuators that regulate the physical variable. Based on what is detected by the sensors, embedded system will control the actuators to perform some output action. Okay, one example for input devices are, as you see in mobile phones, there are keyboards or push button switches, okay, or on-screen keyboards that you might have. And examples for output devices are LEDs, which indicate some action, or LCD displays, liquid crystal displays, or some buzzers, which make some noise or sound. Okay, in that case, we call it sound. Piezoelectric buzzers are examples for output devices. Okay, apart from sensors and actuators, we also have the memory, which holds the software. The software, which is called the firmware, which is built by the company that is producing it. It is responsible for holding the control algorithm. Control algorithm is nothing but the program and other important configuration details. Okay, for most of the embedded systems, the memory for storing the algorithm or configuration data is of fixed type, which is a kind of ROM. ROM stands for read-only memory. So ROM is used to store the program or the control algorithm. So ROM is also called the program memory. Okay, it is not available for the end user for modifications. The end user cannot change any contents in the ROM. That's why it is called read-only memory. The data can only be read from that, but the user cannot make any changes into that. The memory is protected from unwanted user interaction by implementing some kind of memory protection mechanism. Okay, so the part of memory that is reserved for ROM is protected. That is, user cannot change any data in the ROM. Some examples or some types of memories which is used as program memory are OTP. OTP stands for one-time programmable memory. One-time programmable memory. Then PROM stands for programmable read-only memory. Then UV-EPROM stands for ultraviolet erasable programmable ROM. Okay, EEPROM is electrically erasable programmable ROM. Then flash memory. So we will see each of these types later when we discuss memory part. Okay, so these are some types of ROM, read-only memory. So apart from this, there is also another type of memory that is called RAM. RAM stands for random access memory, which is also called read-write memory. So it is called the working memory. So some data, some variables, it should have been stored somewhere, which are used for some arithmetic or logic operations. The system requires some temporary memory for performing arithmetic operations or control algorithm execution. So this type of memory is called RAM, or it is also called the working memory. So different types of RAM are static RAM or dynamic RAM, that is SRAM and DRAM as it is written here. SRAM stands for static RAM, DRAM stands for dynamic RAM, and non-volatile RAM. Okay, NVRAM is non-volatile RAM. Normally, RAM, the contents of RAM will be erased when the power goes off. That's why the RAM is called the volatile memory, whereas contents of ROM will be preserved even when there is no power. So it's called non-volatile memory. So this non-volatile RAM is a kind of RAM. The structure is the type of RAM, but it is non-volatile because it is backed up by a battery actually. So it is a non-volatile RAM. So this also, when we see the classification of memory, this NVRAM is also shown in ROM because it is non-volatile. Still, its structure and construction is based on the construction of, or it is like a RAM actually, based on the construction. So that's why we have three different types of RAM: SRAM, DRAM, and NVRAM. So this is about the memory. Next, apart from these, we have some communication interfaces, which is essential for communicating with the different subsystems of the embedded systems and also with the embedded system with the external world. For this, there can be some onboard communication interfaces like I2C, SPI, UART. We will see all of this in the next topics. Or it could be some external communication like infrared or Bluetooth or Wi-Fi or Zigbee, or maybe your GPRS, 2G, 4G, all those things. Okay, so these come under external communication interfaces. And again, these could be some wired interfaces as well as wireless interfaces, depending on what you use. Okay, so this is about the typical embedded system. Okay, you have to explain about the elements, different elements of an embedded system, and each part in this block diagram. Okay, the system core, then what are the inputs and outputs, sensors and actuators, then the memory, what is there in the memory, types of memory, then communication interface, and some other things which are required. Next, we have the core of the embedded system. So as we have seen, as the main part of the embedded system, we have the system core. The embedded systems are domain and application specific, and they are built around a central core. The core, it might fall into any one of the following categories. That is, it can be a general purpose and domain specific processors. In that, we have three types, again, microprocessors, microcontrollers, and digital signal processors. Or it can be application specific integrated circuits, we call it ASICs, or it can be a programmable logic devices, we call them PLDs. In that, again, there are two types actually, CPLD and FPGA, that is complex programmable logic devices, and field programmable gate arrays. So they come under programmable logic devices. Or it may be commercial off-the-shelf components, which we call COTS. So when we design the embedded system, we have to choose a particular processor or a core which might fall in any of these categories depending on the application. Then we have certain differences between microprocessors and microcontroller. So this microprocessor or microcontroller, they can be the core of embedded system. A microprocessor, as we have discussed previously, it is a silicon chip, or it is a chip representing a CPU, central processing unit, which is capable of performing arithmetic as well as logical operations. That means there is an ALU inside it according to a predefined set of instructions. So what we have to understand is that a microprocessor is just a processor on a single chip. On the other hand, there is a microcontroller which has got a CPU along with all other things for a computer to function on its own. And all these things are integrated on a single chip. So a microcontroller is a highly integrated chip that contains a CPU, a scratchpad RAM, special and general purpose register arrays, on-chip ROM or flash memory for program storage, timer and interrupt control units, and dedicated IO ports. That means it has got, along with CPU, it has got RAM, ROM, certain special registers, then timer and interrupt control units, and even IO ports, all these things on a single chip. Whereas a processor is just a processor on a chip, and all other things, they have to be connected externally. So these are some of the differences which are tabulated. So microprocessor, as we have discussed, these are the definition of microprocessor and microcontroller. It is a silicon chip representing a CPU, a central processing unit, which is capable of performing arithmetic and logic operations according to some instructions. Whereas a microcontroller is a highly integrated chip that contains a CPU, scratchpad RAM, registers, that is special and general purpose register arrays, on-chip ROM or flash memory for storing the program, timer and interrupt control units, and dedicated IO ports. RAM is random access memory. It is also called read-write memory, where data is stored, and ROM is read-only memory, where program is stored. And all these are present in the same chip where the CPU is present inside microcontroller. Microprocessor is a dependent unit. That means it cannot function on its own. It requires a combination of other chips like timers, program and data memory chips, interrupt controllers, IO ports, and all of the things for functioning. It is a self-contained unit. Microcontroller is a self-contained unit. It doesn't require external interrupt controller, timer, UART, and other interfaces for its functioning. It's also called a computer on a chip. Microcontroller is also called a computer on a chip. Most of the time, it is general purpose in design and operation, whereas in microcontroller, it is mostly application oriented or domain specific. So in embedded systems, in most of the cases, we use microcontrollers. Microprocessor doesn't contain a built-in IO port. The IO port means where we connect input and output devices. The IO port functionality, it needs to be implemented with the help of external programmable peripheral interface chips like 8255. So we need to connect a chip which can provide IO port functionality to the microprocessor. Whereas the microcontroller, they contain built-in IO ports which can be operated as a single 8-bit, 16-bit, or 32-bit ports, or as individual port bits. Microprocessors are normally targeted for high-end market where performance is important, whereas microcontroller is targeted for embedded market where performance is not so critical. In microprocessor, there are very limited power saving options compared to microcontrollers, whereas in microcontrollers, it has a lot of power saving features. So these are briefly the differences between microprocessors and microcontrollers. So this diagram gives a clear indication of how microprocessor is different from microcontroller. What you can see on the left, this is a chip that is a general purpose microprocessor. Inside the microprocessor, we will have arithmetic and logic unit and control unit. So if you want to use microprocessor in an embedded system, all other things have to be connected externally, like RAM, ROM, then input output ports, then timer and serial communication port. They have to be connected externally through some buses. Okay, so to get the address of these, we have address bus, and to get the data, we have data bus. Whereas if you consider a microcontroller, so along with CPU, there is memory, that is RAM and ROM and IO ports, timer and serial communication port, everything embedded into a single chip. Whereas here, only the processor is on a chip and other things are connected externally. In microcontroller, all these things are there on a single chip. Then we have certain differences based on the architecture of processors and controllers. The first is based on the instruction set, that is, we have RISC and CISC processors or controllers. So what are these? What does RISC stand for? RISC stands for Reduced Instruction Set Computing, and CISC stands for Complex Instruction Set Computing. As the name itself suggests, RISC is Reduced Instruction Set Computing. That means the number of instructions are reduced. So the RISC processors or controllers, they have less number of instructions, reduced number of instructions, or lesser number of instructions, normally in the range of say 30 to 40 instructions. Okay, not more than that. Your ARM microcontrollers, they are an example for RISC machines, RISC processor controllers. There we have, depending on which type of microcontroller or microprocessor you use, which type of ARM processor you use, there are certain reduced or lesser number of instructions. One example you can take, another example you can take is Atmel microcontrollers. Atmel AVR is a name of a microcontroller. Its instruction set has only 32 instructions, very less instructions. Okay, but they can do the task as any other microprocessor or controller, but you need to write more number of instructions for that, more number of instructions, but they have less instructions. The instruction set has lesser number of instructions. So if you want to perform a task, you need to write a larger code. Okay, that will be the drawback. So CISC, it stands for Complex Instruction Set Computing. That means the instructions are complex in nature and they have more number of instructions. It is instruction set is complex and instructions, number of instructions are high. The 8051 microcontroller is a CISC architecture or CISC microcontroller. Its instruction set has 255 number of instructions. Okay, it has 255 instructions. So advantage of using CISC is the code size becomes less. Okay, there are multiple instructions, the code size becomes less. Whereas RISC, there are lesser number of instructions in the instruction set, but for a particular task, you need to write more number of instructions. Then we will see the differences. Yeah, RISC, there are lesser number of instructions. CISC, there are greater number or more number of instructions. And in RISC, there is instruction pipelining, and that's why we have increased execution speed. You know what is pipelining? I have explained in the class previously, right? Pipelining means whenever a present instruction is being executed, the next instruction can be fetched. That means pipelining. So with that, you can increase the speed of execution. In RISC, it is by default, instruction pipelining is available. But in CISC, generally, there will be no instruction pipelining feature. But there are exceptions like 8051, there is instruction pipeline. Okay, then another difference is in RISC, there is orthogonal instruction set. What do you mean by orthogonal instruction set is any addressing mode can be used for any instruction. That is called orthogonal instruction set. That it allows each instruction to operate on any register and use any addressing mode. Whereas in CISC, it is non-orthogonal instruction set. That means all instructions are not allowed to operate on any register and use any addressing mode. There are some restrictions. So it is instruction specific. You can use only certain instructions for certain registers for certain addressing modes. So the instruction set is said to be non-orthogonal instruction set. Whereas in RISC architecture, there are no such restrictions. Any registers can be used for any addressing mode. Okay, so that's the point here. Next one is operations are performed on registers only. The only memory or operations are load and store. So if at all you want to add two numbers which are there in the memory location, first thing you have to do is you have to copy both the numbers into the registers, into the microprocessor or microcontroller, then perform the operation and then store the results back into the memory. So you cannot do addition or subtraction or any other operation on memory. You can do operations only in the registers. Whereas in CISC architecture, operations are performed on registers or memory, depending on the instruction. In case of RISC, a large number of registers are available. Okay, large number of registers are available. Whereas in case of CISC, there are only a limited number of general purpose registers. Okay, that's one thing. In case of RISC, the programmer needs to write more code to execute a task. This is what I said. The number of instructions are less, but the instructions do simple tasks actually. So if you want to perform a complex task, you need to write more number of code, more number of lines of code to execute a task, since the instructions are simpler ones. Whereas in case of CISC, the instructions are like macros in C language. That means some small functions. A programmer can achieve the desired functionality with a single instruction, which in turn provides the effect of using more simpler single instructions in RISC. Then in RISC, we have single fixed length instructions. All the instructions are of same length. Okay, are same length. For example, if it's a 32-bit processor or controller, it will have all 32-bit instructions or all 16-bit instructions, something like that. Whereas in case of CISC, there are variable length instructions because it depends on the complexity of the instruction. If it's a very complex instruction, it will have more number of bytes. Otherwise, it will have lesser number of bytes. So what do you mean by length in instruction is each instruction will be stored in the memory in the form of bytes, right? In the form of in machine language. That means in terms of in binary format. So different length instruction means some instruction may take only 8 bits, some instruction may take 16 bits, some instruction may take 32 bits. So depending on the complexity of the instruction, the length of the instruction will vary. Okay, then RISC has less silicon usage and the pin count. That means number of pins in a RISC processor controller will be less. Less silicon usage means its size will be less. Okay, whereas in case of CISC, it has got more silicon usage because it has some extra hardware for complex instruction decoding. The instructions are complex. To decode that, we need additional decoder logic. Okay, that's why more silicon is used in case of CISC microprocessor or microcontroller. And in RISC, we have only Harvard architecture, and CISC can be both Harvard and Von-Neumann architecture. Harvard architecture, as you know, it is having separate space for instruction and data memory. Okay, that means the instruction bus and data bus, they are separate. You can access parallelly instructions and data, they can be accessed parallelly, whereas in Von-Neumann architecture both are accessed using the same bus. So parallel fetching of instruction and data cannot be done in case of Von-Neumann architecture. So CISC can have both Harvard and Von-Neumann, whereas RISC has only Harvard architecture. Your 8051 is an example for CISC and Harvard architecture. Okay, your ARM microcontrollers are example for RISC and Harvard architecture. Whereas your microprocessors that you have in your PCs and all, they normally have Von-Neumann architecture or rather some modified Harvard architecture. So 8086 is an example. It has Von-Neumann architecture, but it is also CISC in nature. Whereas 8051 has Harvard architecture, it is CISC in nature. So there are different types of microprocessor or microcontroller based on the instruction set. That is RISC and CISC. If asked in the exam, you should be able to list down these differences technically. Next kind of types of architecture are based on, as we have discussed it at the end, the same thing, that is Harvard and Von-Neumann architecture. So as you know, Harvard architecture, or first we'll see what is Von-Neumann architecture. It is also called Princeton architecture because it was developed by person John Von-Neumann, who was working in Princeton University. Okay, so here they have a single common bus for fetching both instructions and data. So you cannot fetch both instructions and data simultaneously. If you want to perform a particular operation, first you have to fetch the instruction, then you have to fetch the data required by the instruction, right? So it cannot happen simultaneously. So because they share a single common bus for both of them. The program instructions and the data, they are stored in the same memory or common main memory. In the memory also, there is no bifurcation or separation between data memory and code memory. It is same common main memory. Both the instructions or the code and the data required by the instructions, both are there in the same memory. Okay, first they fetch an instruction and then they fetch the data that is required by the instruction from the same common main memory. The two separate fetches, they slow down the operation of the controller. That is one disadvantage of Von-Neumann architecture. Whereas in Harvard architecture, they have separate data bus and instruction bus. Okay, so with this, we can transfer the data and program simultaneously. Data and the program is the code simultaneously on their respective data bus and instruction bus. The data memory can be read and written while the program memory is being accessed. So simultaneous operation is allowed here. So these separated data memory and code memory buses, they allow one instruction to execute while the next instruction is fetched. So that is called prefetching. When the present instruction is being executed, the next instruction is fetched. That is called prefetching of a particular instruction. So this allows for pipelining. Okay. So prefetch, theoretically, it allows much faster execution than the Von-Neumann architecture, because there the prefetch is not allowed. In case of, these are the differences given specifically. In case of Harvard architecture, there are separate buses for instruction and data fetching, whereas in case of Von-Neumann architecture, there is a single shared bus for instruction and data fetching. You can see here, there is a single bus. Okay, there is a single memory. There is no distinction between program memory and data memory. The IO memory and CPU, they are connected to a same bus. If you want to access instruction, it is accessed from the same memory. If you want to access data, that is also accessed from the same memory through the same bus. Whereas in case of Harvard architecture, there is a separate program memory and another data memory. Okay, so there is a different bus for program and different bus for data. So this is easier to pipeline. So high performance can be achieved. Low performance compared to Harvard architecture because there is no pipelining. In case of Harvard, it is comparatively higher cost because separate memories are required here and separate buses. This will add to the cost. Whereas in case of Von-Neumann, it is cheaper because a single bus and single memory is used. Okay, there is no memory alignment problems because there are separate program and data memories. The data will not get mixed with the program memory. Whereas in case of Von-Neumann, it allows for self-modifying codes which are required for aligning the particular data with the memory. Okay, aligning means normally when you store data in the memory, it should start from a particular address which is divisible by 4, or if it is a 32-bit microcontroller, it has to be divisible by 32. The last number, it has to be 0, so that it is divisible by 4, right? So you cannot store the data in any location you want. An address should be divisible by a particular width of that particular microcontroller or processor. If it's a 32-bit, then the address has to be a number that is divisible by 32. That problems arise in Harvard architecture, Von-Neumann architecture, because the memory is shared between data and program. Whereas here, data is in data memory, you have only data. In between, there is no instructions or codes. In program memory, there are only programs or codes. There are no data. Okay, so those alignment problems won't occur in Harvard architecture. The same thing, since data and program memory are stored in different locations, there is no chances of accidental corruption of program memory. Okay, so in between data memory, you will not be storing, in between program memory, you will not be putting any data. So there is no corruption of program. If the program gets corrupted, the system will halt, right? It cannot execute further. Whereas in case of Von-Neumann architecture, they are on the same chip. So there are chances for accidental corruption of program memory. If something is stored in between program memory, if some data is put, the program memory gets erased, so it cannot work, right? In that case, what happens is we will have to use some memory protection schemes so that some part of the memory will not be accessible for data and something like that. So those complex things are not there in Harvard architecture because we are separating the program and data memory. So chances of data corrupting the program is totally avoided. Okay, so these are the differences between Harvard and Von-Neumann architecture.